Bismillah ar-Rahman ar-Rahim. Dear students, ladies and gentlemen, Assalamu alaikum. So my today's topic will be, can you hear me? If you please, anybody unmute mic and tell me everything is okay with Zoom.
Yes,
Yes, sir.
Screen share is also running.
Yes, sir.
yes,
Okay, thank you. Now mute your mic and listen to my lecture, please. Now, in this lecture, we will do three problems related to impulse turbines. That is 11 point, example 11.1, 11.2, 11.3. 11.1 and 2 is about velocity triangles, construct velocity triangles and find out what is required. And example 11.3 is about calculation of blade heights. So first of all, you will see that example 11.1, the velocity problem is the velocity of the steam leaving the nozzle of an impulse turbine is 900 meters per second. That is CV is given. Then you can see that the nozzle angle is 20. The blade velocity is 300 meters per second and blade velocity coefficient is 0.07. Why blade velocity coefficient is given? That means if you know the relative velocity at entrance, you can calculate velocity, the relative velocity at the outlet of the blade because of this factor. Because this factor, this coefficient is the ratio of the relative velocity at exit divided by relative velocity at the inlet, and this accounts for the friction in the blade. If blade is frictionless, then this coefficient is equal to 1. So entrance relative velocity is equal to exit relative velocity. Now, but in this case, it is 0.7. Now, calculate for the mass flow rate of 1 kg per second. Usually, m dot, if it is not given, you can assume, you can calculate power output and efficiency and everything for 1 kg per second mass flow rate and symmetrical braiding. M dot is equal to 1 kg per second. Symmetrical braiding, when we say that symmetrical braiding, it means that braid angle at inlet is equal to braid angle at the outlet. So beta 1, beta I is equal to beta E. So now what is required? These are 5 items which you have to calculate. Blade inlet angle, that's beta I. Driving force on the beam, that is formula if you remember. This is work component, change in work component delta CW multiplied by CB. And the axial thrust, this is delta CF. And diagram power is equal to delta, this is the delta CW multiplied by CB. So now the diagram efficiency is equal to work output divided by the kinetic energy given to the steam in the outlet of the nozzle. That is C1 square by 2. So this is the equation, this is the problem and what is required. We will solve by writing given data first. So in this problem is given CV, blade velocity 300 meters per second. This is tangential velocity of the blade. It's not rotating velocity, it is tangential linear velocity at the periphery of the blade. So 300 meters per second. CAI, absolute velocity at the inlet of the steam, 900 meters per second. Angle at the entrance, angle of steam velocity at the inlet is alpha I. This is nozzle angle. This is also called as nozzle angle because nozzle injects the steam jet at this angle to the turbine blade. This is 20 degree. K is the velocity coefficient. This is the ratio of the relative velocity at outlet divided by relative velocity at the inlet. M dot, I have written M dot because it is difficult for me in Word to put dot at the top of the M. So read it M at the dot at the top of the M. So I write it M dot. In the book it is printed, so it is easy. So M over dot, but here in Word, I don't know, there must be some method, but it is very lengthy. So I don't want to go in that detail. So M dot is equal to 1 kg per second. Now, what is the methodology? And how to solve this problem? This is called methodology. From the data given in the problem, velocity triangles are drawn. This is the method. First of all, you need to draw velocity triangles to the scale. It's very important, not as a rough sketch. You need geometry box with tools, geometrical tools like scale, protractor, and compass, and eraser, and very sharp pencil. And it usually gets broken when you draw the line. Line should be very thin and accurate. So you need graph paper for scaling. Graph paper is made small division is equal to 1 millimeter and one big division is equal to 1 centimeter. So with the help of this, you can scale the velocity, and then you can draw this triangle A, B. This is OAB. This is velocity triangle at the inlet of the plane. OAC, velocity triangle at the outlet of the plane. You know, if you know BI, you can, first of all, we draw OA, line OA. This is actually horizontal line we draw. This is tangential velocity of the blade, CB. 300 meters per second is given. So how much should be the length of this triangle, this side of the triangle OA? This is according to scale what you take. So better, for example, if we take 100 meters per second is equal to 10 mm, then this will be 300 divided by 100. So that means you will need 3 centimeter. And in 30 centimeter, 30 millimeter, yeah, 3 centimeter length of OA on the scale in the graph paper. Then with the help of protractor, with this horizontal line, you will draw angle beta I 29.4. If it is not given, let us start from here. CAI is given. CAI is given. So with the help of protractor, put one pin of the protector here and pencil side, open the pencil with on the linear scale. 900 millimeter means 100 अगर 900 meter per second. So 100 meter per second हमने अगर 1 सेंटीमीटर लिया तो 9 सेंटीमीटर लॉन्ग कंपास खोलेंगे और एक आर्क लगा देंगे. उसके बाद हमने CRI हमें दिया है या कैलकुलेट करेंगे, तो ये CRI लेकर इसको काटेंगे. So then you can draw OAB. Otherwise, if angle beta I is given or calculated, you can draw here in this diagram is 29 degree and 24 minutes. We can draw this triangle, this line AB. So similarly, in this triangle OAC, if we know CR, we know this angle. This angle was given here, velocity angle, so this line could be drawn, that angle. So in order to draw this, we need CAE, exit velocity, absolute. This is CRE, this is CAE. We need CAE. Since we know that it is symmetrical braiding, the beta I must be equal to beta E. So this angle OAC is known, so that is equal to 29. So in this way, you can draw this. On this triangle, once it is drawn, these two triangles at inlet and outlet, now from this diagram, you can take a linear scale, futta, और उसकी मदद से नापें कि भाई ये distance कितना है, C से लेकर B तक horizontal distance कितना है, तो this is 927.7 meter per second. तो अगर हमने scale लिया था 100 वाला, तो 100 से तो 9.277 यानी 9.28 के करीब ये मिलीमीटर यानी सेंटीमीटर 9.28 सेंटीमीटर के करीब लेंथ होगी, और दिस इज इक्वल टू 927.7 मीटर पर सेकंड डेल्टा CW. This is the world component of the velocity. This velocity is responsible for rotating the wheel. So power output के लिए ये फॉर्मूला यूज होता है. इस velocity को 927.7 को CV इस velocity 300 से multiply करेंगे, you will get work out. So that is blade diagram work. So similarly, we can, if angles are required, we can measure with the help of protractor what is beta I, what is alpha. Alpha is given or not given. If it is not given, you can measure from here. So data taken from this diagram for this problem is given here. Data taken from velocity triangle drawn to the scale. So this is beta I is not given, it is measured with the help of protractor after drawing this triangle, and it will be 29 degree and 24 minutes. CRI, relative velocity at the inlet, this is CRI. This is also not given. We measure through the scale when triangle is drawn, and this will become 625 with the help of a scale. That means 6.26 centimeter. Or CFI, flow component of velocity is axial component of velocity, which drives the flow of the steam through the blade rows. So this VB is the CFI, and this EC is CFE. So from here we can measure length and scale it. So this length should be 3.07 centimeter, which is 307 millimeter per second, and this length should be 2.15 centimeter, which is equal to 2.15 meter per second velocity. So this is how we draw the triangle and solve the problem, and we measure scale quantities from here, whatever is required. Then we do some calculations. For example, applying cosine law. Cosine law I have also given in the beginning of this chapter. So revision of calculus, revision of algebra, and revision of geometry. So in there it was given cosine formula, which you can revise, and with the help of cosine formula we can calculate CRI, and this CRI square is equal to CI square plus CD square minus 2CD CI cos alpha I. So these quantities are mentioned here, and you calculate CRI 626.5 meter per second. So actually this triangle was possible to draw because of this angle. Alpha is given because of this velocity 900 was given, and calculated velocity this was given, and velocity CB was given. So in this problem, CB was given 300, CI was given 900, alpha was given 20 degree, and this was calculated with the help of cosine law, and this is how triangle completed. Is it clear to you now? So I am requesting you to please, when I'll give you assignment to solve this problem, you are not supposed to just copy it and draw the triangle with freehand without scale. You have to take things which I have told you: graph paper, pencil, putta, sharpener, eraser, everything, a protector, divider, everything should be with you, and you have to draw accordingly, which I am telling you now. And you have to draw and see with your own hand how these velocities are calculated. Now CRI is calculated with the help of formula, then triangle is drawn. There is another formula of geometry which is called as sine rule of the triangles. So according to sine rule, we will solve OAB triangle. This is CAI divided by sine angle OAB, CRI divided by sine alpha I. From here, sine OAB is equal to this. So from here, we can calculate sine beta. From here, sine beta I is equal to CI sine alpha divided by CRI. Now we know sine alpha, we know CAI, we know CRI, just calculated above. And putting these values, we can calculate sine beta I. So beta I we did not know, so we calculated with the help of cosine law and sine law. And then beta I is this is sine inverse 0.491, and this is equal to 29 degree. With the help of Casio calculator, you can find what is the angle. 29 degree, 24 minutes. Your calculator will show you Casio hai, jo bhi hai, Toshiba hai. So you know this angle beta is also calculated. So now let's go to next calculation. Next calculation, part 2. We are required to calculate driving force on the wheel. Driving force on the wheel is m dot delta CW. M dot is equal to 1. So delta CW we've taken from the diagram, and this is equal to 1 multiplied by 927.7, and this is equal to Newton per kg per second. This is driving force. So delta CW taken from the scale, and side AD of the triangle. CR is calculated from this formula. There's a velocity coefficient K is equal to 0.7. CRI calculated above by cosine law, and with the help of this we calculate CRE first. Then side AD. Side AD of the triangle calculated as CRI cos beta I. With the help of this, you can find 545.8 side AD. Then CR exit is equal to cos beta exit, and this is equal to 289. Now we know all velocity from these. Once two triangles are drawn, we can find delta CW is delta CW at inlet delta CW at outlet, CW at inlet plus CW at outlet. So this is delta CW, and this is 927.7. And graphically in the triangle, velocity triangle, it is shown this. Side C, this length CB. You draw to the scale these two triangles, you will get measure this in centimeters and find out, multiply with the scale, and you will get 927.7 delta CW. This was part 2. So in part 2, we want to calculate driving force. For driving force, we need delta CW multiplied by mass flow rate, which is 1 kg per second, and we got 927.9 Newton per kg per second driving force on the blade. Now, calculation item 3 is we want to calculate axial thrust. Axial thrust and diagram power unit per unit mass flow rate. So for that we need from the triangle CFI to calculate CFI. You can calculate with formula. You can measure to the scale as I've told you about. So by formula it will be CRI sine beta I. CRI is already known, beta is already known. So now we can calculate 307. Otherwise we can measure directly from the to the scale velocity triangle. Then CFE is equal to CRE sine beta E, and this is equal to 215.3. So change in axial component of the velocity, which is called flow velocity CF. So delta CF is equal to difference of about CF exit minus CF inlet. So CF exit 307.6, CF inlet 215.3. Now difference is 92.3. This is delta CF. This is the force which is responsible for axial thrust on the bearing. In axial direction, we will move, push by force with this force. Now, therefore, axial then equation 11.4, we find axial thrust with the help of m dot. Axial force multiplied by mass flow rate, change in it. This is linear change of momentum. M dot delta CF. M dot multiplied by change in velocity is change in momentum linearly. So in axial direction, change in momentum is equal to force applied in axial direction, and this is equal to 92.3 Newton per kg per second force. This is called axial thrust. Now, diagram efficiency का formula is CB multiplied by delta CW. Delta CW we already calculated. CB is given 300. So B divided by 1000 because we want to convert watt into kilowatt. So without dividing by 10 raised to 3, the answer will be in watts. And now by dividing 10 raised to 3, answer will be in kilowatt. And here is the answer in front of you, 278.3 kilowatts. Now part 5 of the question is equation 11.6, diagram efficiency is calculated with the help of this. So CB multiplied by delta CW is the work output or work done by the steam on the blade divided by kinetic energy of the steam coming out of the nozzle, that is CAI square by 2. So 2 will go up and CI square will remain in the denominator, and we get the answer 0.687 or 68.7%. With this, we have finished this calculation, and now let's go to another example, 11.2. So this is the continuation. This is the first stage of a turbine in a 2-row velocity compounded impulse wheel. Steam velocity at inlet is 600 meters per second. The mean blade velocity is 120 meters per second, and blade velocity coefficient is 0.9. The nozzle angle is given 16 degree, and exit angle is given. So here I have summarized given data, and here I have given the solution methodology. Again, we will draw velocity diagram and do some calculations, whatever is possible. In simple cases, we can calculate some items, other items with the help of those items, and given data in the question, we draw these triangles. This is for blade 1. The difference in this problem and that previous problem is that previous problem was single stage. only one rotating wheel. Here there are two rotating wheels, which is called Curtis turbine. One set of nozzles and one set of two blades, moving blades installed on one wheel. They move together. In between these two moving blades is a stationary blade or fixed blade. So this is velocity triangle at the one moving blade, this is velocity diagram at the other moving blade. And then data scaled from the velocity diagram. Once velocity diagram is done, with the help of protector, you will measure alpha E and beta I2, alpha E1 and beta I2. 1 means blade row 1, 2 means blade row 2, or E means exit, I means inlet. So these are the angles in front of you. Beta I1 is given in the problem, 20 degree. Now, with the help of K, that is velocity coefficient 0.9, you can calculate CI2, which is equal to CI2. This is about fixed blade. At fixed blade, CAEI is actually inlet to the fixed blade, and CAE2 is the outlet to the fixed blade, and this is actually inlet to the second moving blade. So that's why it's written CAE2. So it's equal to K times CAE1. So now you know velocity entering to the second row of the moving blades, and first row का ये data है, first row का और second row का ये data आ गया आपके पास with the help of these velocity triangles to the scale. And from first row we get velocity CF, axial component also at inlet and outlet, and second row inlet and outlet axial component velocity CF. Now calculations are done here. Beta I20, so beta I1 is equal to 20, beta I2 is equal to 34 from the scale. We have done already the triangle. So driving force is equal to your formula m dot CW. Here is calculation, and all other are done with the help of formulas in front of you. Now item 3 is similarly done with the help of formulas because data is already available from the velocity triangle drawn. What we need here is power output के लिए we need driving force हमने calculate कर ली, delta CW1, delta CW in wheel 1, delta CW in the wheel 2, rotating wheel 2, and this is this much, and power output is given as CB multiplied by delta CW, and energy supplied to the wheel is m dot CI square by 2. So diagram efficiency is equal to power output divided by energy supplied to the wheel, and this is 77.9% diagram efficiency. Now part 4 is maximum diagram efficiency. We have derived a formula in last classes that for Curtis turbine, maximum diagram efficiency is equal to cos square alpha I2, which is calculated here. Then example 3 starts. This is about same 11.2. Previous data will be repeated here, and further data is given m dot is equal to 5 kg per second, and nozzle height. In this problem, you will calculate nozzle height. So nozzle height is 25 mm, and specific volume is given at the outlet with the nozzle 0.375 kg per meter of steam, and nozzle pitch is given 25 mm. Pitch means a distance between two consecutive blades is called pitch. So what you have to calculate is, one more thing is given, thickness of the blade at the exit. Thickness of the blade at the exit is required to calculate exit area. So length of the nozzle, you have to calculate a nozzle arc. Nozzle arc. What is nozzle arc? You know, in impulse turbine, a nozzle does not cover the whole circumference of the rotating blades. Only partially it covers set of nozzle, 4-5 नोजल इधर 4-5 नोजल दूसरे एंगल पे 4-5 दूसरे, तो ये सारे के सारे ब्लेड्स के ऊपर नोजल फिक्स नहीं किए जाते, उसके आमने सामने नहीं होते, बल्कि वो एक खास पोर्शन में होते हैं. उस पोर्शन को हम कहते हैं नोजल आर्क लेंथ. सो लेंथ ऑफ द नोजल आर्क. सो इस पार्शियल एडमिशन, इसको हम पार्शियल एडमिशन कहते हैं, क्योंकि वेलोसिटी जो है वो स्ट्रीम जो है पार्शियली एडमिट होती है, पूरे के पूरे रोटेटिंग ब्लेड में नहीं होती. तो टाइम इज ऑलमोस्ट ओवर. You read, go through. I have given theory also. So ये theory आप repeat करेंगे, पढ़ेंगे. इसकी मदद से हमने ये formula derive किया है. M dot V is equal to this 11.17, 11.18. जब ये दो formula derive हो जाएंगे, सब कर दिए हमने आपके सामने, तो फिर formula इसका ये है. solution here, calculation here, when you go through it, you do by yourself with your own handwriting, then you will understand it. And I'll display to you all these lectures, including this solution. Thank you very much. Time is over.
सर आपकी
Any
आवाज नहीं
question,
ठीक आ
please? Any question you have?
No, sir.
Okay, thank you. Attendance, CR, please make the attendance.
Okay,
Bye-bye,
sir.
sir.